So this week, we will discuss two topics that are, for the most part, completely disconnected with what you learned in the first 2 weeks. We'll spend about half of the week discussing anomalies, and the second half of the week, approximately, discussing instantons. So for the first 3 or so lectures, we'll discuss anomalies. And what are anomalies? So anomalies are quantum effects that spoil classical symmetries. So you've seen a brief introduction to anomalies in the first week of this course, where you learned about the conformal anomaly, and on your homework you saw a problem regarding 2D massless QED, the chiral anomaly. And so in this part of the course, we'll go into some more detail and discuss some general methods for finding when a symmetry is anomalous. And so today we're just going to go through a simple example. We're going to go back to the massless QED example that you saw in your homework and discuss that in some more details to get some intuition for when anomalies arise, why they arise, and then we'll see several other ways to compute anomalies over the next few days. So we'll derive anomalies from the path integral, where from the path integral perspective, you can think of anomalies as arising when the theory has a symmetry, the classical action is invariant under that symmetry, but an anomaly can arise if the measure is not invariant. And then you can also find anomalies through perturbation theory, through Feynman diagrams, and so we'll also look at that. So before we go into the 2D massless QED example, I just want to say a few general things about anomalies. So anomalies arise when two contradictory requirements clash. So, for example, in 2D massless QED, classically there are two symmetries, vector and axial symmetry. Quantum mechanically, it's impossible to maintain both of those symmetries, and we have to choose one. And usually, one of the contradictory requirements is gauge invariance. So vector current conservation is closely related to the gauge invariance of the theory. So that's the requirement that we're going to choose to satisfy. So if we want vector current conservation and gauge invariance, then we have to sacrifice axial current conservation. Another point to keep in mind, and I'll discuss this in more detail in this example we're going to go through, is anomalies have both IR and UV aspects. So they have IR aspects in that they can be seen by low energy observers. We don't need to do very high energy experiments to see that there's an anomaly. But in a sense, the reason that we have an anomaly is that is related to the impossibility of finding a UV regulator that satisfies, that respects the symmetry. So, and these IR and UV aspects are closely related. We'll see that in some detail in the example we're going to go through today. A final point before we start to go through this example is that there are two different types of anomalies. We can have a global symmetry that becomes anomalous. Or we can have a gauge anomaly. So there's nothing inherently wrong if a global symmetry is anomalous. And in fact, this can lead to some very interesting physics and can be used to explain things like the decay of the neutral ion to two photons. On the other hand, if a gauge symmetry is anomalous, this can have serious implications and destroy the consistency of the theory. We saw in QFT2 a little bit that gauge symmetry is necessary for renormalization and unitarity. So if we have an anomalous gauge symmetry, that can ruin the theory. And so we'll see in a few lectures that whether or not a gauge symmetry is anomalous is related to the matter content of the theory. So the absence of gauge anomalies puts constraints on what matter you're allowed to couple to your gauge bosons. So that's a bit about where we're going and some things to keep in mind as we go through this example and see some of these aspects of anomalies in a very in simplest case. In particular, we'll see this IR and UV aspects of this anomaly. Okay. So what we're going to show is that although classically the Schwinger model, which is massless 2D QED, although classically this theory has a axial symmetry, that symmetry is broken by quantum effects. And so to see that, first let's recall some facts from QFT1. So in QFT1, we studied the free Dirac spinner in 4D in detail. And so if m equals 0, the Lagrangian is just I psi bar d slash psi, and this is invariant under two symmetries. A vector symmetry and an axial symmetry. And so Noether's theorem tells us that each of these symmetries has associated with it a conserved current. And the conserved currents are, for the vector current, which I'll denote either as J sub V or just J, is psi bar gamma mu psi, and the axial current either JA or J5. It's the same thing with the gamma 5. And both of these currents are conserved. So this is hopefully familiar to you from UFT1. And basically none of this depends on, none of this will change if we go to 2D instead of 4D. This is unchanged. In 2D. So going from 4D to 2D doesn't change it, and neither does adding an electromagnetic field. So the model we're interested in is this model. And so we're in 2D. And in 2D, just to establish notation, we have that the gamma matrices satisfy the usual anti-commutation relations. And I'm going to choose G mu nu to be +1 -1. And we can choose a basis for the gamma matrices so that they're just related to the Pauli matrices. Choose gamma 0 to be sigma 2, gamma 1 to be I sigma 1. And then gamma 5 is just gamma 0, gamma 1, which is sigma 3. So with this basis for the gamma matrices, we can break up psi into positive and negative parallelity parts. So gamma 5 psi is just plus psi plus minus psi minus. And so another way to write this is gamma 5, the projection operators, is plus or minus projection operators acting on psi, where the projection operators are just the same as you're used to, the left and right projection operators. So really nothing changes if we go from 4D to 2D so far, except for the gamma matrices are now 2 by 2. So we can expand at the fermionic part, or Lagrangian. If we do that, what we see is that there is no mixing between psi plus and psi minus. So that means that the number currents for psi plus and minus are separately conserved. Okay. And if we set the gauge field to 0, we see that the free fermion equation of motion is just this. So the solutions are just waves moving to the left or right at the speed of light. All right, so that's just a brief review of the classical theory. So now what we want to figure out is what happens quantum mechanically. And what we're going to show is that so we're going to treat the fermions quantum mechanically, and the gauge field classically we'll just assume it's a background gauge field, and we're going to slowly turn it on. And what we're going to show is that as we turn on the gauge field, the axial current is not conserved. So that's where we're going. And before we do that, we need to think a bit about what gauge fields to consider. And also, a point that's worth making is that in 2D, the Coulomb potential grows linearly. So that means that there is confinement for any value of the coupling if space is infinite. So if we do just work in 1 plus 1 dimensional Minkowski space, then we're necessarily working in a strongly coupled regime. So at least at low energies, which makes this model interesting for other purposes. But if we want to do treat the gauge field as a perturbation, then this is not a very good model. But fortunately, we can fix this rather easily just by compactifying on a circle. And if E naught L is much less than 1, then this is perturbative. So note that we're in 2 dimensions, so the coupling is dimensionful. So the coupling has to have dimension 1 in order for the units to work out. Okay. So if we're in compactified space, Then we can write the gauge fields as some linear combination of signs in the spatial direction and some arbitrary function in the arbitrary function of time. So most general gauge field configuration would just be a sum of terms like this. So we have gauge freedom, and we can use that gauge freedom to set A to be at least A1 to be a constant. So let's just consider a single term. Then we can use a gauge transformation. We choose alpha t of x to be L over 2 pi n A1 of t sine of 2 pi n over L x. Then A mu goes to A mu plus t mu alpha. That lets us set A1 of t and x just to be some function of time only. So through a gauge transformation, we can make the spatial component depend only on time. But this is not the only type of gauge transformations we can do. There are also large gauge transformations. In the sense that they're not continuously connected to the identity. We choose alpha to be 2 pi n over L x. So this is not periodic. Which may worry you, but all that we really care about is that the gauge field itself is periodic. And after we take a derivative of 2 pi n over Lx, that's just a constant, which is periodic. So this respects the periodicity of A mu. So this tells us that A1 plus 2 pi n over L are gauge equivalent, are all gauge equivalent. So putting this together, this tells us that A1 lives on a circle of circumference two pi over L. And it's spatially constant. And that's there's no possible gauge transformation we can use to get rid of a constant A1. Because if we integrate the gauge field around the circle, the spatial circle from 0 to L, that's a gauge invariant Wilson loop. So it can't get rid of it by gauge transformation. Okay. So now we want to understand the quantum mechanics of this theory. And we're going to work in the adiabatic approximation and treat the gauge fields as external and slowly varying. We're also going to set A0 to 0. So the reason we're going to set A0 to 0 is because A0 is responsible for the Coulomb interaction. So it controls the interactions between the fermions. So it's and we want to work in the limit where the interactions are weak. EL is much less than 1, so its effect will be subleading. So in this approximation, the Dirac equation becomes 0 plus gamma 5 d1 minus I a1 phi is equal to 0. So all I've done here is just multiplied by minus I gamma 0. And so this is the equation we want to solve. And so we're interested in the energy eigenstates. So the stationary state wave functions should be proportional to e to the minus I en t times psi n of x. The periodicity tells us that psi n of x should be proportional to e to the 2 pi I n x over L. And it's straightforward just to plug this into the Dirac equation and solve for the energies. So we'll have different energies for the psi plus and psi minus, which we can just denote as E plus and E minus. If we plug this in, we just get plus or minus 2 pi n over L minus plus A1. Okay. So now, now that we found the spectrum, we can, in the Dirac picture, draw what the ground state looks like for A1 equals 0. So we sketch E versus P. Our right movers, or the psi pluses, will have all of the negative energy states filled, and all of the positive energy states empty. And the states are just equally spaced by an amount 2 pi over L. Similarly, for the left movers, so this is with A1 equals 0. We have equally spaced energy states that are all filled for the negative energy states and empty for the positive energy states. So now we can ask what happens if we increase A1 adiabatically from 0 to 2 pi L. So if we increase A1 from 0 to 2 pi over L, the spectrum is mapped onto itself. So we'll just shift n by plus or minus 1, depending on if we're talking about the right movers or the left movers. So what will happen is the so we increase this. The left movers will all the states in the left moving spectrum will shift up by 1. And for the right movers, we have minus sign, so I'll move down by 1. And so what we'll end up with is, if we do turn on the gauge fields adiabatically, the occupation numbers will be unchanged. So we'll end up with an empty state in the right movers, and an extra filled state for the left movers compared to our vacuum state, which is the original picture over here. Sorry. Okay. Any questions so far? So what we've done by turning on the gauge fields is we've created one left moving particle, and one right-moving antiparticle. We have a So the electric charge is unchanged. We have one extra particle and one extra antiparticle. But the axial charge Q5 is changed by 2 units. And we can see this by, the left-moving particle we can assign to have axial charge -1, and so the right-moving particle will have charge +1, and right-moving antiparticle then has axial charge of -1. So delta Q5 is -2. And it'll be useful to rewrite this in terms of the current. And to do that, we know that if we had changed A1 from 0 to 4 pi over L, we'd get a change in the axial charge of -4 units. So this -2 is equal to -L over pi, to be proportional to the change in the gauge field, which tells us that if we divide this all by delta T, Q5 dot is -L over pi A1 dot. And so we can write the axial charge as, in the usual way, just as the integral of the 0th component of the axial current. And L times A1, the integral of epsilon 0 mu A mu dx. So putting this together, we see that this is just since A0 is 0, this is just the same as this equation here. So this is the axial, the anomalous non-conservation current for the anomalous non-conservation equation. Or the axial current. we expected this was 0 classically, and we see we have a non-zero right-hand side. Okay, so that's the result, and let's spend a few minutes discussing what happened here and why we got this result. But first, are there any questions on that result? Okay. So a few comments about our derivation. So first comment is that the fact that we had infinite energy levels was crucial to our argument here. So we were able to map the spectrum back onto itself, even though without mapping individual states onto themselves. And that's only be possible if we're changing all of the energy levels in the same direction. That's only possible if there's infinitely many energy levels. So anomalies are really a feature of Q of t. We need infinitely many energy levels. Another point to make here is that although everything I was discussing was really, I was really focusing on what was going on near 0 energy. So we had an extra part. We deduced that there was an extra particle and an extra antiparticle by looking at what was going on near 0 energy in the IR. But implicitly, I was making assumptions about the UV that were crucial to this derivation. So in particular, we made some assumptions about what was going on with the charge in the UV. So we had an implicit UV regulator. So we assumed that at large negative energies, there was no change in the charge, the electric charge. So one way to frame that is we could imagine putting a cutoff at minus lambda on the spectrum. And we assumed that whenever a state crossed from below our cutoff in the left-moving spectrum, went from below our cutoff to above our cutoff in the left-moving spectrum, simultaneously a right-moving state disappeared. So that was implicit in what we were doing. That I said the charge was conserved, and might seem obvious if we just think about what was going on near 0, but that there's something implicit going on in the UV too. And there's no reason a priori that we would have to regulate what's going on in the UV, the right-moving spectrum in the same way as we do in the left-moving spectrum. Could be free to regulate the spectra in left and right-moving spectra in different ways. And if we did that, it's possible we could choose a regulator so that the appearance of a new state above our cutoff in the left-moving spectrum was not correlated with the right-moving spectrum. And in that way, we could come up with a regulator that would preserve the axial current at the cost of not preserving the vector current. So that's possible. We could do that. And it seems like an unnatural choice here. But we'll see tomorrow and Wednesday, we will derive the anomaly in different ways where it won't be so obvious what's the natural choice of a regulator will be that will preserve the symmetries we want to keep. So in this case, vector current conservation is more important to us than axial current conservation because vector current conservation is linked to the gauge symmetry. And so here we see that, and also in this example, we see that there is a link between what's going on in the UV and what's going on in the IR. So there's a direct connection between crossing of the UV cutoff and the crossing of zero energy. The entire spectrum shifts by the same amount. And so that's a general feature of anomalies is they mix the UV and IR. And so where we're going over the next few lectures is we're going to derive the anomaly in several different ways. So tomorrow, what we're going to discuss is anomalies from the path integral. And we'll see in our different ways of deriving the anomaly, some of these aspects will be clear in some derivations and not clear in other derivations. So we'll discuss anomalies from the path integral where and the anomaly you can think of as coming from the non-invariance of the measure under the symmetry. And we'll also discuss anomalies from perturbation theory and Feynman diagrams. And in perturbation theory, it will become abundantly clear that the anomalies arise due to conflicting requirements of our theory. So here it's not picking a UV regulator that preserves the axial symmetry without preserving the vector symmetry seems a little unnatural, and in perturbation theory, none of the regulators will seem that any more natural than the other, and so we'll see that really anomalies come when we have to choose which symmetries we want to keep. And then on Wednesday, we'll really discuss non-abelian anomalies. And see how we have to choose the matter in order to cancel off non-abelian anomalies. So non-abelian anomalies are always gauge anomalies, which I briefly argued are very bad and ruin the consistency of the theory. So that's where we're going over the next few days. Any questions?
Yes, could you repeat what was the problem if we just left if we didn't introduce a regulator?
So if we didn't introduce a regulator, then you can ask the question of how do we know that there's nothing funny going on in the far in the very low energy negative energy states. So in principle, it might seem natural to you that charge should be conserved at very low energies at the bottom part of the spectrum. But the spectrum goes down arbitrarily far, and how can we say anything for sure? So that's the kind of subtlety we need to be very careful about when we're dealing with anomalies. So in this case, it seems like we can make sense of the theory without introducing a regulator, but for instance, in our path integral derivation, the anomaly, we won't be able to make any progress without introducing a regulator. We'll have ambiguous quantities, 0 times infinity, that we can't make sense of without introducing a regulator. In the computed from Feynman diagrams, we'll have divergent integrals that we can't make sense of without introducing a regulator. So we're essentially forced to. In the other examples here, it's a little bit less transparent, but again, you want to say for sure that charge is conserved at very large negative energies. We need to introduce a regulator to make that explicit. Any other questions? All right, I'll see you tomorrow.